So let's start. Hello everyone, I'm Cafe Observer. Today I will be moderator for this session, and today it's our first session with Sanan Suleymanli. Sanan Bey, thank you very much for accepting our invitation and being mentor in this course. And before starting this main part of the session, I wanted to give brief information about Sanan Bey. Sanan Suleymanli pursued his bachelor degree at Kafkas University, majoring in chemical engineering. He also holds a master's degree in process engineering from Delft University of Technology. He participated for several internship programs at Petrokimya, Amek Foster Wheeler, Soccer Polymer, and Technip FMC. Since August 2019, he has been working as process engineer for Soccer in HAOR modernization and reconstruction project. And today he will talk about oil refinery process. And just one more thing, if you have any questions, please do not hesitate to ask, or you can write in the chat box. At the end, he will answer to your questions. So please, Sanan Bey, can you start?
Good afternoon, Kafia Hanım. I think you can hear me and see me well. And good afternoon, dear participants. It's a pleasure for me to be part of this project. That's why I would like to thank the Kafia Hanım for inviting me, not only inviting me, but convincing me to give a session about refinery processes. And now I feel happy that I am here with you. I also had a chance to watch some of the previous sessions, such as the separation processes and the membrane technology, and I think they were quite useful. I hope you will also find this session as useful as the others. Today I will talk about the refinery processes. On your screen you can see the refinery in Thailand, which is obviously that it is not just a small plant. It's a complex. It's a big complex that consisting of different the units, different processes, and I think I will explain the processes briefly, and you can ask me your questions. Please do not hesitate to disturb me, to stop me and ask your questions. I will try to answer your questions as much as possible. This whole scheme can be summarized in this block diagram. So here what we see, we see the different blocks which are connected to each other, and we have so many streams here. We have so many products which are shown in blue, and we have also so many intermediate products. Now you look at the scheme, you look at the block flow diagram, and you see that how complicated it is, but in fact it is not. However, it is really impossible to learn the processes at the refinery by only memorizing. Why? Because you are engineers, and engineers do not memorize. Just before starting my session, you will see this block flow diagram a few times during the session, and we will discuss the processes each time. Before starting the lecture, I would like to show you how to learn graph. So sometimes people think that if they read and memorize, they can learn, but this is a shorter way to learn. However, if you want to learn deeply and for a long term, you need to take the longer way, which means that you should read, listen, see. That's what you are doing right now, and think what you are listening, analyze what you are thinking, and understand what you are analyzing. If you apply this way, then you can learn. Then the question is that how to think, how to analyze, and how to understand. You will ask questions. You will ask two types of questions, two different types of questions. The first one is how. The second one is why. If you ask why questions too many times for yourself and try to answer that one, you will understand the theoretical part of the any concepts, not only the engineering, refining processes. You can apply this way for any concept. When you ask how question, then you start to think about the application of your theory. And then you analyze, you understand. This way, you really learn. Is that end? No. Once you learn, you don't want to forget it. You want to remember it. The way to remember is to reproduce it. How we reproduce? We take notes during the classes, and then we read our notes again and again. That's one way. Another way can be doing the homework assignments, which we do at the universities. And the most effective way of reproducing is teaching. You share your knowledge, you teach others, and this way you learn more than the ones you teach. I will show you also a pyramid that shows how we learn, and at the end you can see that 95% of what we teach to others. If you share your knowledge, you learn more and more. Just being honest, I will tell you something. Because of the time limitation, I didn't prepare my slides myself. I just used the different sources. The one of them was at this petroleum refining course on Udemy platform. Although I am working as a process engineer at the refinery, I found this course really useful just to revise the processes, and I use this course material mostly to prepare my presentation. However, I also use the different sources, different books to complete my presentation. Oil reserves. Why we have oil refinery? Because we have a lot of oil reserves. Here you can see that the most oil reserves can be found in the Venezuela, Saudi Arabia, then Canada, etc. If we have so many oil reserves, then we also should have the oil refineries, too many. And this shows the map view of the oil reserves. Here again you can see that we have the most oil reserves in Venezuela, the Saudi Arabia, Iran, Canada, etc. And this is the statistics from BP Statistical Review of World Energy 2018. What we see that comparing the years 1997, 2007, and 2017, we can see the sharp increase in proved reserves from 1,162,000 million barrels in 1997 to the nearly 1,700,000 million barrels in 2017. You can, if you are interested, you can check the market analysis, supply chain. There are a lot of reports on internet. However, I don't want to go deep of this part because we have a lot to discuss in terms of the engineering. So this is the map view of the world crude oil refiners. There are hundreds of oil refiners, big or small refiners throughout the whole world. It means that we have also a lot of oil reserves. It means that we are going to refine oil and use the products to get the energy for a long time. Then what's the crude oil? Crude oil is a multi-component mixture consisting of more than 108 compounds. So in the next slide we will see that the crude oil is mainly composed of the hydrocarbons and also other impurities, water, etc. And that's why we have to refine oil, because if we cannot use the crude oil effectively without refining. You can ask what is refining. The refining is just changing the shape or bringing the feedstock to useful products. It's not only the oil is refined. milk also is refined. Milk is refined and we produce different products. The nuts is refined. So different feedstock can be refined, but today we will talk about the crude oil refining. And the petroleum refining refers to the separation as well as the reactive processes to yield various valuable products. Before starting the refining, we can classify our oil. So here you can see that we have light sweet to heavy sour oil. So what is light? Light means that it is light oil, low density oil. API is from 35 to 60. And you can see that we can find a specific gravity using this formula, which means that once API increases, specific gravity decreases. So higher API means the lower density of crude oil. That's why it is considered light oil. For your information, the API of the crude oil we are refining right now at Heydar Aliyev Oil Refinery is around 30. 30 API means that we have medium density. And that corresponds to around 0.875 the specific gravity. What about the sweet and sour? Sweet and sour represent the sulfur content of crude oil. So we have the from 0 to 0.5 weight%, it is sweet. If you have more than 0.5 weight% sulfur in the crude oil, that is the sour. Okay, what does it tell us? Why we need to classify our oil for light and sweet? Before answering the question, we can check the composition of crude oil. So you can see that from 1 barrel, which is around 159 liters of crude oil, we can produce around 46% of gasoline, 9% of jet fuel, which is also called the kerosene, and 26% of diesel and other fuel. Of course, these numbers are not exact. These numbers can be different for different types of the crude oil, and also what we want to produce more. If you want to produce the less gasoline, then we design our process in a such way that this number will be lower, but diesel will be higher, for instance. But in fact, you can see that the light fuels or the useful fuels is around 80% of crude oil. That is the most money the refiners earn from. That's why the refiners try to produce as much as gasoline, jet fuel, and diesel in order to make money. Other products, the lubricants, heavy fuel oil, asphalt, bitumen, are considered the heavy products, which in fact have low contribution to profit. This is the typical petroleum refining scheme. You can see that here we have crude oil and enters the heater. After that, we have the distillation column and we produce the different product. Now, I will so what we said that there are around 108 components in the crude oil, and the carbon number can start from C1 to C70 plus. That's why it's a mixture of really light components till heavy components. We have to separate it. We separate it, but what our products are not pure substances either. Our products are also mixtures, but in a certain range. So we have C1 and C2, which we call dry gas. We have C3 and C4, which we call LPG. So from C1 to C4, we have the gases. And then starting from C5, we have the liquid products. We have C5 to C10, it is naphtha. You can also call it the gasoline. Here we can see the light naphtha and heavy naphtha. And after what? After C10, we have the kerosene cut. And then we have the from C14 to C20, diesel fuels, lubricating oils, fuels for ship. And then the final one is C70 plus. It is residue which we use for asphaltene, bitumen, etc. So you can ask what does C10 means? C10 means that all different types of the molecules with 10 carbon number. It can be alkanes, alkenes, paraffins, aromatics, etc. All of them are included in this one. If you have any questions, you can ask. Okay, I continue again the same, the BFD. Now it should be more similar to you. Now you are already familiarized with some of the terms. For instance, what we said that we have LPGs, butanes. Butane is the C4, LPGs is C4 and C3 and C4. We have the refinery fuel, C1 and C2, jet fuel, kerosene, diesel oil, fuel oil, which also can be considered as diesel. And then asphalt is coke. We have the different streams of the gasoline from different units. And then we blend them in the pool. So each block, we called it unit. So each unit does not mean the one piece of equipment. Depending on the size and the complexity of the unit, there can be from 50 to 500 pieces of equipment. So when we say that the unit, it is small plant in the refinery. Now, I would like to ask you something. What we said that if you want to learn, we have to think, analyze, and understand. For this, we have to ask questions. Now, I want to ask you to write down why question or how question. Just look at the scheme, block flow diagram. Whatever you want to ask. Start with the why question or how. Make a question and write in the chat, please. So this is the block flow diagram. What you should do, just to check the block flow diagram and ask your question starting with why.
Rasul Amirov asks for each unit between 50 and 500. Okay, he asks.
Yes, for instance, we have the atmospheric distillation unit, and here we have more than 500 pieces of equipment. What I mean by piece, it is pump, compressor, distillation column, any types of the equipment can be found there. Because the atmospheric distillation column is one of the biggest units of the refinery. But if you go to a smaller unit, then you can have from 50 to the 100. For instance, the amine treating, no, we have the amine treating unit is something small. you have around the 75 pieces of equipment there. I do not see any questions there. Okay, I will ask questions. For instance, you have a few hydrotreaters here. There's one here, there's one here, there's one here. Then I can ask why we have so many hydrotreaters, or how a hydrotreater works. Another question is that why we have so many gasoline streams? Why did we don't have only one? Why did we have so many? This can be the examples to ask questions. If you ask questions yourself, you start to think. Otherwise, you listen without thinking. I will continue. What is petroleum refining? Petroleum refiners have a goal to convert as much as a barrel of crude oil into transportation fuels. Which were the transportation fuels? Gasoline, jet fuel, and diesel, which is around 80%. This transport, and also we can count the LPG. These transportation fuels have boiling point between 25 and 0.350 Celsius. We will talk about the boiling points of the products later. And as I said before, refiners produce many profitable products. The high volume profitable products are the transportation fuels. This is the crude distillation unit, which we will talk about later. And also, if you remember, I asked the question why we should classify the crude types. We have sweet. So what we said, we had sweet and sour. We had light and heavy. This is what we learned about the crude types. So if you have a sweet and light crude, then we need the less complex refinery to refine this crude. However, if you have heavier and sour crude, it means that we need more complex. Why? Because if it is sour, you have to clean that. To clean more sulfur, we need the higher design capacities or more complex equipment, higher pressure, higher temperature, etc. So if we have the lighter crude, it means that we have more transportation fuels in the crude oil. But if you have heavier, then it means that we have less. What we want to do to crack the heavier part of this crude into the lighter hydrocarbons, which are considered transportation fuels. And cracking units are more complex. And this, and here what I explained is written. But however, in the future, what we can expect that we will end light crude as time passes, and we have to use the heavier the crude in 20, 30, or 40 years. In this case, this will then make the refiners require processing the entire barrel of crude rather than just the material boiling, below. So you will use the higher temperatures, higher pressures, and it will cost more to refine the heavy crude. These are the examples of the petroleum products, which we see in the previous one. We have the gases, naphtha, kerosene, light gas oil, heavy gas oil. This is the diesel and residue. And you can find the photos of the different the products. So gasoline, this is the transparent. You have the kerosene, it's also transparent. The diesel fuel, you have the yellowish color, and as it becomes the heavier, the color also becomes the darker. These are the different types of the products which are obtained through crude, because the light fuels such as the C3, C4, and light naphtha can be sent to petrochemical complex. Here in Azerbaijan, we send the light naphtha to Azerkimya, In Azerkime, they produce the ethylene, and then from ethylene, they send ethylene to Sokar Polymer. Sokar Polymer produces the propylene, and from propylene, we can have, let's say, the bottle or other products. So from chemicals, which is also produced from crude oil, we can have the nylon, styrene, polyester. We have the liquid fuels, lubes, residuals. Residuals can be used for bunker C, asphalt, roofing material. So as you can see, there is no loss in crude. We use the lightest component from C1 to C2 as a fuel gas to the heaviest component as asphaltene or roofing material. The process overview. So as you can see, crude oil and gas is extracted from the well, and then of course it has a primary and secondary separation before it is sent to the refinery. Once it is sent to the refinery, it is desalted. We also have desalters in our refinery, and refinery is our main scope. Today's scope, we will talk about the processes there. And what is petroleum refining? In the refinery, there are both physical processes and chemical processes. The physical processes can be the distillation, atmospheric distillation, vacuum distillation as a process unit. But of course, we have the different types of the separation or adsorption in each unit as a single unit operation. We have the alkylation, isomerization, cracking, reforming. These can be the examples for the chemical processes. We can separate the refinery processes into three parts. The first part is a separation. Why separation? Because crude is a mixture of C1 to C70 plus, and we have to separate it first. Once we separate, we want to convert what heavy products to light products. Why we convert heavy product to light product? Because light products are transportation fuels, which helps to make higher profit. And then after all, we have the storage and blending. We blend the different streams as I showed in the block flow diagram for gasoline, and also we have some additives to diesel, jet fuel, etc. Is that all? No. Why? Because we have also treating. What is treating? Treating you can think as cleaning. Cleaning from S content, cleaning from nitrogen content, also some oxygen, etc. Why? Because we have some standards, we have some product spec for the transportation fuels and also other products. For instance, if you want to produce the Euro 5 fuel, you have the not 10 ppm sulfur limitation. So what was the sulfur content of crude oil? We said for sweet, we said it is 0.5 weight percent. So which means that it is 5,000 ppm S content in the crude oil, but our final product, it can be diesel or gasoline, should have the 10 ppm sulfur content. That's why we need to have the treating processes. And these treating processes will remove the heteroatom impurities from refinery streams and blend stocks, remove aromatics compound from refinery streams. We will talk about the treating more later. Okay, again, coming to back to this block flow diagram, let's see how many hydrotreaters we have. We have one, we have second one, the third one, at least, and the fourth one here. So what I asked before, I asked that why we don't have hydrotreater here. You put hydrotreater here, and you just treat the whole crude. Then you separate it. Wouldn't it be possible? Yeah, it might be possible, but we have to think that we have a mixture of from 1 to 70 plus hydrocarbon in our crude oil. And it means that from gases to really heavy residue. We need to have a special process, so higher temperature and pressure. And also the residues, can poison the catalyst, because the hydrogen process is catalytic process. It can poison the catalyst in the short term. And also it has the 5,000 ppm sulfur. So this all make having the one single hydrotreating before distillation unit. That's why what we do, we first separate, then we have the different processes for each types of the product as a hydrotreater. But whatever you have there, you cannot sell your product without hydrotreating. You cannot sell your product with so high sulfur content. This block flow diagram can be different. You can see the different versions on internet, but these are all similar. All have the hydrotreating units, all have atmospheric distillation, vacuum distillation, gas separation, catalytic cracking. I can also show them here. We have the vacuum distillation, crude distillation, FCC, which is the catalytic cracking. We have the catalytic reforming. So these are all similar to each other, but how the streams are aligned between the units can be different. Once again, what is a unit? Each single block is called a unit in the refinery. Unit operations. So here, what you see here in these block flow diagrams are these types of the unit operations, which are the crude distillation unit, vacuum distillation unit, thermal crackers. Now the delayed coker units are used mostly, hydrotreaters, catalytic cracking, naphtha splitter, etc. Now we are going to talk about these unit operations briefly. Separation processes. So what I said before, that we can classify the processes in the refinery in a few steps. The first part is the separation processes, which can be distillation, absorption, extraction, crystallization, adsorption. Now you can find these separation processes in each unit. In each unit you have a separate distillation column, you have a reboiler, etc. And this primary distillation, we use the atmospheric distillation, because that is the first unit of the refinery. And we have also a secondary distillation, vacuum distillation. And conversion processes are catalytic reforming, isomerization, alkylation, hydrocracking, catalytic cracking, etc.
Sanan Bey, we have a question in chat
Yes.
box. Rasul Amirov asks, what is reformer?
Thank you, Rasul, for your question. I will talk about the catalytic reforming process in future slides. And finishing processes. Sweetening. Sweetening is used for gases, because if gas has the H2S content, we have to remove H2S content before we use the gas as a fuel. Why? Because if you burn H2S, it will convert to SO2, it will go to atmosphere, and when we have the rain, we have acidic rain. That's why we have to sweet the gases before we burn. And also hydrotreatment. We have the hydrotreatment with hydrogen, for instance, the RSSR plus H2 hydrogenation reaction, and here we have the product plus H2S. This H2S leaves the unit hydrotreatment process as a gas in the gas, dry gas, and then it is sweetened. We have also the environmental processes, such as the acid gas processing, stack gas processing, wastewater treatment process, which is which is built right now at the Baku Refinery. We will have a new wastewater treatment process, and who watched the membrane technology yesterday and the first lecture of the membrane technology, there we talked about or Zehra Hanım talked about the membrane application in wastewater treatment processes. Now, everything starts from atmospheric distillation. What is atmospheric distillation? This is also a different view of the block flow diagram. And what I mean that each unit has so many pieces of equipment is this one. For instance, the catalytic reforming unit. This is really simplified the PFD, but the real PFD has so many pieces of equipment, or the isomerization unit, alkylation unit. Each part has a different, each block is a different unit, each block has different processes. Crude distillation unit. The crude coming to the refinery first goes into the dissolters. In the dissolters, we first add the wash water, we add the, I will write it down, we add the wash water, we add the demulsifier, and then we create emulsion, and then we separate all the water in the crude from crude oil. So you can see effluent water go to wastewater treatment plant, and then the crude oil which was separated from the water is first preheated and is sent to the heater, and at around the 390 degrees it enters the atmospheric distillation column. And in atmospheric distillation column we separate the products which we saw in block flow diagram: gases, light naphtha, heavy naphtha, kerosene, diesel, atmospheric gas oil. This is also can be considered as diesel. You can think like that: light diesel, heavy diesel. And then we have the atmospheric residue to vacuum unit, vacuum distillation unit. So what was our first aim? To separate it, to separate the components in the crude oil. Once we separate, what we do? We have the residue, which is heavy, but we want to extract the transportation fuel, such as the diesel, from the vacuum. We will talk about the vacuum distillation unit later. And operating conditions, the temperature at the entrance of the furnace, where the crude enters, is around 200 and 280 degrees. And after the furnace, it is heated to 330 or 370 degrees. The pressure is around 1 bar G, as it can be seen from its name, atmospheric distillation unit. This is the flow diagram, a simplified process flow diagram of the crude distillation unit. It's the same atmospheric distillation or crude distillation unit. We have the same products again here, and this residue goes to the VDU, vacuum distillation unit. What happens to these products? They are sent to hydrotreater. And sour water, what does it mean, sour water? We have too high H2S content in the water. It can be sent to sour water stripper. And in sour water stripper, H2S and water is separated. Water is sent to wastewater treatment plant, where we treat the water, and the water is sent to Caspian Sea. And H2S is sent to sulfur production unit. So we produce sulfur from H2S. If you have any questions, you can stop me and ask. Okay, I will ask you why it is 2 atm here. Because previously we said that we have 1 bar G, but now it says that 2 atm. 2 atm is 2.026 bar. Any idea?
Hello.
Hello, Ilkin.
I think because of reflux.
Not really.
Okay.
Any other idea?
Can you ask again? I didn't catch exactly.
We have 2 atm here, or let's say 2 bar. But in the previous slide, we say that we have 1 bar G. Why? Why we have such difference? Okay, I will answer. So you are probably familiar with absolute pressure.
Yes.
And gauge pressure. And P absolute is P gauge plus P atmospheric. So if you have G here, it means that it is 1 bar G. It is gauge pressure, 1 bar G inside, which is equal to 2 atmospheric or 2 bar absolute pressure. But they are the same. So this has the same number. This is the reason. And here I can see that the Ilkin asked that this water means that we have water in the feed. Yes, we have water in the feed. Yes, we have desalters. We try to separate the water as much as possible, but we have also the water left in the feed. And also from the hydrogenation processes, if there is a oxygen, that oxygen can react with the water and not oxygen gas, oxygen as an element that can react with H2 and we produce more H2O. There was another question. How many bars are in 1 bar G? 1 bar G is 1 bar. So 1 bar G is 1 bar plus 1 atm. This gives you 1 bar or 1 bar absolute. And 1 atm can be taken as 1 bar. So if you want to be exact, 1 atm is bar. Why? Because 1 bar is 10 to the power 5 Pascal. 1 atm is Pascal. This is about the pressure, the side section of our session. And then what we said, we have the residue. Residue is sent to vacuum distillation unit. And in vacuum distillation unit, it is 20, the pressure is from 25 to 40 millimeter Hg. What does it mean? 1 bar G is 750 millimeter Hg. So if you want to find this one, let's say the 40 mHg, you will have around the 0.05 bar G. And then I want to ask you why vacuum distillation unit? Why we have the vacuum condition to separate the light products from heavier ones?
Hi, I can answer this question.
Yes, please.
Because of the if we separate in the previous one, in this case we should need a higher temperature, approximately 500 over the 500. But in the vacuum distillation, we have here injector, and we create the vacuum phase. In this case, we decrease and we can separate the in for approximately 400 temperature. But if separate it higher temperature, in this case, our bond, carbon-carbon bond or others, can be
Can be broken.
Can be broken, and that's why we need the vacuum column, because in here we have injectors. This can help to us to create vacuum phase, and after the vacuum phase we need a normal, we can separate normal temperature what we need.
Thank you very much, Leman, for your answer. That was the exact answer to my question. So if we don't have the vacuum condition, then this temperature would be more than 500 Celsius. But as you know, when the pressure decreases, so when pressure decreases, the boiling point also decreases. That's why we create the vacuum condition in order to boil or to evaporate the light ends in the heavy ends, and then to separate it. Also, as Leman said, another answer is that if you have a 550 Celsius degree process, there will hydrocracking or cracking processes will start immediately. That's what we don't want. And 550 degrees Celsius also means that higher energy. The refinery is really energy to be conserved plant. You want to conserve the energy as much as possible, and you want to use the energy as much as effectively. So we have the different products from the VDO, which are the light vacuum gas oil, LVGO, heavy vacuum gas oil, and heavy residue. Vacuum residue is the heaviest part of the crude oil, which is sent to thermal cracking or coking unit, or it can be sent to bitumen unit to produce bitumen. Here you can see the process. We have the steam ejectors, which help us to create the vacuum condition inside the vacuum distillation column, and we have the atmospheric residue, or we can call it AR. Why we give steam there? Because it has higher viscosity, it has higher density. In order to pump it easily, we give the steam in the atmospheric residue. And then we have the special packages inside the vacuum distillation unit in order to separate the light vacuum gas oil, heavy vacuum gas oil, and the vacuum residue. We have also sometimes the lighter end, diesel, which is so low. Okay, we talked about the atmospheric distillation unit. We said that the atmospheric residue went to vacuum distillation unit. We have the vacuum residue. Vacuum residue goes to delayed coking. Vacuum residue goes to bitumen unit. Here we produce asphalt. We will produce coke. I will talk about later. We have the light vacuum gas oil. We have the heavy vacuum gas oil, and then atmospheric gas oil, which is sent to FCC, hydrotreater, and then FCC. And the rest are, as you can see, diesel oil is sent to diesel hydrotreater, and then it is sent to the product storage, and after adding some additives, it is sold. And also jet fuel, we have the special type of we don't use the hydrotreater here, but we use the caustic and amine to clean the sulfur content of the jet fuel, that's why it is called the Merox treater. And then after the jet fuel is cleaned, it is also sent for sales. We will talk about the light naphtha and heavy naphtha now. First of all, gas treating units. As you can see, we have gases. When we say gas, we talk about the C1 to C4. And other gases all come to gas processing unit. In gas processing unit, what we want to do is to split the products. We want to split to C1 and C2, C3, C4. C1 and C2 is dry gas. C3 is propane, propylene fraction. C4 is butane, butylene fraction. We want to split them. And then we also want to clean them. We can use the amine treating for dry gases. We can use the Merox process, that is with caustic plus amine to clean the PPF and BBF streams. So gas treating units, that is done with the amine. As you can see, we have the sour gas. What is sour? Sour means that gas with high sulfur content. And we have the lean amine here. Gas is given from bottom of the column, and the lean amine is given from top of the column. And then lean amine absorbs the S sulfur content and leaves the column as rich amine. Rich amine is sent to the amine regeneration column, or to the different unit, amine regeneration unit. Here we have the sweet gas product, which can be used as fuel gas. And then after amine is regenerated, it is sent back to the amine treating unit. And operating conditions are between the 150 and 3000 PCIG. Feedstock is the gas products from cracking, fuel gas with H2S, and the products, as I said, are clean fuel gas, hydrogen sulfide. So what happens to hydrogen sulfide? Let's go back. Hydrogen sulfide from sour water stripper. It goes to sulfur plant. With the Klaus technology, we can produce sulfur. Sulfur can be solid or liquid. What will happen to sulfur? Then we can produce it in a different plant, sulfuric acid, for instance. But in our refinery, we will just sell it to consumers. So now we are done with gas. We are done with diesel, atmospheric gas oil, and atmospheric residue, and jet fuel. We have left the light naphtha and heavy naphtha. Hydrotreaters, as I told you before, the sulfur content in the crude is significantly high. What is it? 0.8% for sweet. And if it is bigger than 0.58%, that is sour. Products from CDU and VDU consist of significant amount of sulfur, and sulfur removal is accomplished to remove the sulfur as H2S using nitrogen. So HD hydrotreating or hydrodesulfurization can be used, but it is not only hydrodesulfurization, it is also HDN, hydronitrogenation, because not only the sulfur content is removed, but also the N or nitrogen content is removed. So HDS, sulfur content is removed as H2S, nitrogen content is removed as NH3. How? With the reaction of hydrogen. So various hydrotreaters are used. We already talked about this one. So you can use the hydrotreaters or for feedstock of different units or for products of different units. And also for kerosene hydrotreater, as I said, that now mostly the caustic Merox unit is used to treat the kerosene, which means that we don't use the hydrogen. Instead, we use a caustic and amine solution to treat the kerosene. This is the typical process for the hydrotreating. As you can see, we have the recycled gas compressor. We compress the H2 to around 40, 50 bar G, and we have feed here. It is mixed. It is first preheated, then after the fired heater, it is heated to 300 to 400 degrees Celsius, and then in the fixed bed reactor we have the hydrogenation, hydrodesulfurization, hydronitrogenation reaction. And as you know, hydrogenation reactions, let's say carbohydrogen plus H2 is combination reactions, which means that they are exothermic. That means we have to control the temperature really carefully in our reactors. And always H2 is given much more than needed. For instance, 3 times or 4 times than the needed number. And then later on, in the gas separator, H2 is separated, and then it is sent back to recycled gas compressor. And of course, the used H2 hydrogen is made up, which comes from the hydrogen production unit or reforming. We will talk about the reforming, but just remember that the hydrogen comes from reformer unit, or I will write HPU, hydrogen production unit. Once we have the liquid product, it can be diesel for diesel hydrotreater, it can be gasoline for gasoline hydrotreater. It is sent to the stripper, or you can also think as a distillation column with reflux and reboiler. And here we separate the products. For instance, this is the binary distillation. We have only 2 products, sour gas. What is sour gas? Gas with H2S content, and desulfurized product. Or we can have the several products such as diesel, naphtha, etc. Again, sour water. Where sour water is sent? Anyone can tell me? What we do with sour water? Sour water is sent to sour water stripper. What we do in sour water stripper? We separate the water and H2S. What we do with water? We send it to wastewater treatment plant, and then from wastewater treatment plant we send to Caspian Sea. What we do with H2S? We send it to sulfur, let's say the recovery or production unit. I will write RU, sulfur recovery unit. Here we produced sulfur. So whatever. So you can have the sour water in different units, in each hydrotreating unit, in catalytic cracking unit, in delayed coker unit. You collect all the sour water stream, and then they're all sent to SVS, sour water stripper. H2S is stripped and sent to sulfur recovery. We produce sulfur. Water is sent to wastewater treatment. We treat the water. We cleaned all the impurity, not impurities, the hydrocarbon or other sulfur content, or we treat it biologically. Then it is sent to Caspian Sea. So again, going back to the yesterday's lecture, if you also have the reverse osmosis for wastewater treatment plant, you can also use that water as a drinkable, potable, drinkable water. So we have only left with naphtha, light naphtha, and heavy naphtha. Naphtha you can also think as gasoline. Naphtha splitter. Why we have naphtha splitter? Because we have here light naphtha, heavy naphtha. But some cases we have just one naphtha stream. If we have one naphtha stream, it should be sent to naphtha splitter. It is sent to naphtha splitter. Here we separate the heavy naphtha from light naphtha. Once we separate it, we can send to heavy light naphtha to isomerization unit, and we send heavy naphtha to reforming. You can also think like CCR, continuous catalytic reforming. Why we do all of them? Because only producing the naphtha or gasoline is not enough for us. We want to have the RON octane number as higher as possible. But we have around the 80s this light naphtha and heavy naphtha from atmospheric distillation unit. That's why we use a naphtha splitter to split the light naphtha from heavy naphtha. We use it, we send it to isomerization unit. From isomerization unit, the final product has around 87 RON, and from CCR you have the RON of 97. And of course, you need to hydrotreat it. So you can have different options: HDT, hydrotreating, naphtha splitter, light naphtha, heavy naphtha. Or second can be the two naphtha splitter, light naphtha. You hydrotreat the light naphtha, and also you have the heavy naphtha. You hydrotreat the heavy naphtha. As I said before, you have the hydrotreating unit for your feedstock or for your products. How it is chosen? It is just design option. You have the feasibility study. You choose which option is better for your process. And reformer. As I said, heavy naphtha is sent to reforming. What is reforming? From its name, we change the shape or the chain of the hydrocarbons. From normal chain, we produce aromatics. Aromatics is produced. Why aromatics is produced? Because aromatics have higher octane number. So feedstock is desulfurized heavy naphtha. The produced light ends, reformer gas, H2. So what we do, reformer gas, we send it to the hydro desulfurization or hydrotreating units and reform it with higher octane number. So this is
Sanan,
the...
we
Yes,
have a
please.
question in chat box. What are the criteria for this choice?
I think that is about this one. So you choose to evaluating your catalyst. For instance, if you have a catalyst for reforming process and which is poisoned heavily by sulfur, you should have the hydrotreating before the reforming. Or I mean that you can also have the HDT here. No, you have the HDT, then you have the CCR, then you have the isome. Because the catalysts in isomerization and catalytic reforming units are poisoned by sulfur content. But as I said, you make the feasibility study, you compare both options in terms of the energy and the other factors, and you decide which one is better for you. For instance, in our refinery, it is this one. First, we have the hydrotreating unit, then we have the naphtha splitter, then light naphtha, heavy naphtha is sent to isomerization unit or catalytic reforming unit. For different refinery, it can be the different case. Hope I could answer your question. Continuing with the reforming unit. So feed, what is feed? It is heavy naphtha. Feed is pumped, preheated, and then is sent to fire heater. Yeah. And as you can see here, we have the 4 reactors, 1, 2, 3, 4, on top of each other. So it is not like, it is series reactors. There are 4 heaters and 4 reactors, but the reactors are on top of each other. It is like one single column. Why we have that one? Because the reforming process is endothermic process, and that's why after each stage we need to heat it again to around this is out the stream, to around the 520 degrees. That is the maximum. The minimum is 493 degrees. Once after, let's say, reactor 4, the temperature decreases, it is again sent to heater, it is heated to the desired, to the required temperature, and second phase reaction, third phase, fourth phase. And after all, you have the product here. We use the heat exchanger to preheat the feed. So heat goes from the products to feed, and then we have cooler, we have gas separator. In gas separator, what we have, we produce net hydrogen. So CCR unit is the main contributor of the hydrogen gas. What we do with net hydrogen, it is sent to hydro treating units. And then this is the reformate. And then reformate has also some gases. That's why it is sent to stabilizer. We separate the off gas. It's the same, nearly the same as dry gas. It is C1 and C2, but it has a little bit content of C3 and C4. But we try to separate the LPG separately. LPG is our product, off gas is our product, and reformate is our product. And reformate has 97 research octane number. It can go as high as the 105, depending on the process conditions, temperature, catalyst activation. So this is about the reforming. The same here, we have the after the reactors, we have the separator. We separate the net gas, fuel gas, and then after the stabilizing section, we have the reformate, net liquid, this is CCR, and light ends to recovery. Finally, we have the fluidized catalytic cracking. We'll go back here. So we have atmospheric gas oil, we have light vacuum gas oil, we have heavy vacuum gas oil. Okay, we separated them, but these are heavy products. What we want to do is that we want to send it to fluid catalytic cracking unit to crack heavy products in order to have the light products. It's one of the most important units of the modern refinery because it adds the value to the refinery. The feedstock is the hydrotreated heavy vacuum gas oil, and the products are the FCC gases, FCC gas oil, gasoline, light naphtha, heavy naphtha, cycle oil. This is diesel. This is the slurry is sent to the late coking unit. So this is really heavy product. We only produce coke from this product. As you can see, it has mainly three sections, the fluid catalytic cracking. The first part is the reactor. This is the reactor. This is the regenerator for the catalyst, and this is the main stabilization column. Here you can see the simplified PFD, process flow diagram of the fluid catalytic cracking process. You have the regenerator, you have the reactor. So riser reactor, why it is called the riser, all the raw oil charge, so let's say vacuum gas oil, VGO, is preheated and with steam in a vapor, as a vapor inlet to the reactor. And as it goes above, we have the catalyst here coming. It mixes with the catalyst and there is a hydrocracking reaction. And the catalyst is regenerated back here. So as you can see, there is a cycle of the catalyst in between the regeneration section and the reaction section. That's why it is called the fluidized. Like you have the solid catalyst, but it is the recirculated in your regeneration and reaction. That's why it is fluidized catalytic bed cracker. If, let's say, the one single reactor with single bed, it is called the bed reactor. Bed reactor is used for hydrotreating processes. What does it mean? There is only catalyst filled once, then you have the process. If you have any problem with the catalyst, you have to stop the process and you fill out the process, fill out the catalyst and fill it again. However, for FCC, for fluid catalytic cracking process, we have the fluidized. It is also the same for the reforming. That's why for reforming, we call it continuous catalytic reforming. And then all the product leave in a gaseous state the reaction and it is sent to fractionator. We have the gases here, gasoline, light gas oil, these are BHOS, diesel, and then clarifier. But heavy gas oil is really heavy diesel, that's why it is sent to delayed coker unit, DCU. And we have also slurry here. Yes, we have slurry. So slurry splitter. We can use the slurry to send it back to the reactor because it has high temperature, or we can also use slurry to send it back to DCU, delayed coker unit, as I showed here. So slurry we can use, we send it to delayed coker unit and produce coke there. This is another scheme of the fluidized catalytic cracking. As you can see there, we have the regeneration, reaction, distillation column, and we have all different types of the products. Another scheme, I just added different schemes to my presentation so that when I send it to you, you can check and compare the different schemes and find the similarities and differences between them. The thermal cracker. Thermal cracker we use for really heavy products. What are they? Feedstock is vacuum residue, or it can be HCO, heavy cycle oil from FCC plus slurry from FCC. So the products are the cracked naphtha. Again, we crack it in a special reaction, cracked gas oil and thermal cracked residue to fuel oil blending. But in modern refineries, we use the delayed coker unit to produce coke. Again, we have the naphtha as a result of the cracking. We have diesel, which are then sent to HT hydrotreating process. But we have also coke, which is used in furnaces. In furnaces such as the metallurgy furnaces. This coke is not loss, but it is cheap. It does not add much value on the refiner profit. However, the delayed coker unit is really important for the refinery. Why? Because, let me go. Delayed coker unit means that I sent my vacuum residue to my delayed coker unit. If I have a problem with delayed coker unit, it means that I do not have much space for vacuum residue. And once the storages are full, I cannot do anything with my vacuum residue. That's why I have to stop the plant. So it is important. There is no loss here, and everything is going for sales. Then for naphtha or the gasoline blending pool, we have the isomerate, let's say octane number of 87. We have the reformate, octane number of the 97. We have the hydrocracked gasoline, octane number of the 92. We have the alkylate and FCC gasoline, 92. It is around 90, if I'm not mistaken. And then it goes to the gasoline blending pool to produce, let's say, the 92 gasoline and 95 gasoline. We do not have it here, but we can also have the MTB unit. MTB unit produce the MTB methyl tertbutyl ether, which has the octane number of 116. Thermal crackers, and then finally we have the blending pools. In blending pools, we can blend the different streams of the gasoline in order to have the 92 or 95 the gasoline with the required spec, or we can have some additives. For instance, we have additives to diesel fuel, we have additives to jet fuel to meet the product specification. Which product specifications we should consider? These are the ACM temperatures, viscosities, octane numbers, flash point, pour point, and these are the product blending pools: LPG, gasoline, gas oil, fuel oil. These are the LPG storage. You can see these are spherical. Question: why these are spherical? For instance, these are the cylindrical storage, but these are spherical for LPG. Any idea? Spherical storage can withstand high pressure. Because C3 and C4 are gas at normal condition. But when it comes to LPG, it means a liquefied petroleum gases. Now, to liquefy it, we need high pressure. And spherical storage can withstand high pressure. But here, the cylindrical storage can have around 5-6 bar G. Up to 10, let's say, but this one can have the 30-40 bar G, even higher if it is required. Again, about the blending pools, the most important blending pool in the refinery complex is the gasoline pool. Why? Because we want to have the specific, the defined octane number for the gasoline we want to sell. The premium and regular gasoline products are prepared by blending appropriate amounts of. So we have the M-butane. These are the different streams: reformate, light naphtha, alkylate, light cracked naphtha. Or we can also add here MTBE. And you can see that it is R plus M divided by 2 method. What does it mean? If you want an octane number, it can be RON, research. It can be MON, motor. And there is a difference of delta is around the 10. For instance, if you have the 97 for this one, for MON you have the 87. And it says that this 87 is the average of these two. So if it only writes the research octane number, it would be probably around the 92, I don't know, 94 or 95 and 98. These two products are by far more the most profit-making products of the modern refinery. So this is the, let's say, the supply chain of the crude oil and the products of the refinery. The crude oil comes to the gathering lines, crude storage tanks, and then from here it is sent to pump station. We have transmit, and finally it is sent to oil refinery. From oil refinery we have the diesel storage, gasoline, and then they are sent to marketing terminal, tanker trucks, and for service. This is the end of my presentation for today. We talked about the refinery processes in general, and also tried to summarize the processes of the main units at the refinery, such as the atmospheric distillation unit, the vacuum distillation unit, fluid catalytic cracking unit, continuous catalytic reforming unit. We also talked briefly about the delayed coking unit. And also, of course, we have the hydrotreating processes throughout the whole refinery. So if you have any questions, please do not hesitate to ask me.
Thank you very much, Sanan Bey. That was a great presentation. There were a lot of information, actually.
Yes, I know.
I actually have a question.
Yes, please.
In one of the slides, you said LPG is kept in spherical tanks, right?
Yes.
But I wonder how the shape of the tank affect the pressure.
So 1 moment. So it comes from let's say the spherical nature of the. So when it is spherical, you can imagine that they are bonded. Let's say the material, whatever the material it is bonded to each other in a systematic way. That's why high pressure, it can withstand high pressure. But when it is cylindrical, there are two parts the shell part and the top and bottom part. This makes the storage less high pressure resistant. So it comes from its geometry, and in each geometry how the material bonded each other.
Okay, thank you very much.
Thank you for your question.
Any other questions?
I will also send the presentation to you with my notes so that you can share with the students. We will have the next session next week. I will tell you the exact time, but what I told you, that if you want to remember what we learned, we should reproduce it. That's why I want to give you just kind of the homework assignment. Just check this block flow diagram again and again after the session or whenever you have time, and try to really understand the processes there. Do you really understand why we have hydrotreating here? Do you really understand why we have the fluid catalytic cracking here, based on what we discussed today? And then just take a separate piece of paper and try to draw block flow diagram with your understanding. Do not memorize it. Memorize and copy, no. Just think from the atmospheric distillation unit, which products we have, then what I need to proceed further, where I should put the fluid catalytic cracking, this kind of stuff. Think and try to construct this block flow diagram yourself. Once you can construct it yourself, then you will understand the processes at the refinery better. And in next sessions, we will go deep of each processes. We will talk through the process flow diagram. Today we mostly use the block flow diagrams, but in the next sessions we will talk through the process flow diagrams of each unit. So if you want to learn more, if you want to understand more, first you have to understand the block flow diagram well. So this is the homework assignment to the students who want to study more.
Rasul Amirov says that I think that pressure is more evenly disturbed. I think it's about the
Spherical
tanks. Yes, and what were the cylinders on the last picture?
You mean this one? Here the cylinders are storage tanks.
64.
Oh, these are also storage tanks here. All the cylinders are storage tanks. So you can ask that why roof is below, because the storage tanks can have the floating roof. That's why when it is empty, the roof goes down. That's why you can see the shell around it. But if the storage tank is full, the roof will go up.
Oh, very interesting. I didn't never.
Yeah, as you can see here, that the storage tank at the center is kind of half filled. That's why roof is belower. But if you look at the other, at the edge here, this one is full. That's why the roof is at the top. It is because for instance, the naphtha can evaporate, and if it evaporates, there is a pressure because of the gases, evaporative gases. So to prevent this one, there is a floating roof. So floating roofs can be also two times, internal and external. If it is internal, you don't see that, but these are the external ones. That's why we see them. To prevent the naphtha light let's say, the hydrocarbons in the naphtha being evaporated.
Thank you very much for your answer. If there is no question, I think we can end the meeting. I also want to say thanks to our attendees for joining our session today.
Thank you very much. Bye.
See you.
See you. Bye.